Welcome to another episode of AI on AI, where we slice through buzzwords and get straight to the code and the corporate boardroom. Today, we're unpacking interpretable robot control with behavior trees and large language models. Buckle up, it's going to be fun.
Great to be here. As someone who runs innovation strategy for a global logistics group, I'm seeing C-suite curiosity explode around this topic, mostly because they finally get to talk to robots in plain English instead of learning arcane command syntaxes.
And from the control system side, it's honestly refreshing. We've been wiring finite state machines for years. Behavior trees let us slot in new modules, almost like Lego Technic, without the spaghetti.
Absolutely. The LLM is now the universal parser that turns that plain English into a behavior tree activation map. Think of it as the Rosetta Stone glued to a decision graph.
I like that image, but let's not gloss over user experience. Natural language isn't always natural. People say go over there and wave their arms. The multimodal bit matters.
Right, and under the hood we're exposing ROS2 services so every node ticks in sync. One mistimed tick and you've got a drone face planting. Seen it, don't recommend it.
Ha! Let's start with the 30-second elevator pitch. Why combine behavior trees with LLMs instead of bolting GPT on top of ROS and calling it a day? In a word, determinism. Pure prompt to action can hallucinate. Wrapping the LLM in a behavior tree adds a guardrail layer. Selector nodes, fallbacks, tick rates. We can enforce battery 20% before flip.
I'd add interpretability. A behavior tree is readable, debuggable, and visually inspectable by non-engineers. That's gold for compliance teams.
And to translate that to business value, auditability reduces operational risk. Remember the 80-20 rule. 80% of downtime cost comes from 20% of unknown behavior incidents. If we can see the tree, we slice that 20%.
Nice. Now a quick technical deep dive. How exactly does query-to-behavior mapping work?
Sure, the LLM operates in a one-shot prompt with a tool list: move, takeoff, person follow. It returns a JSON blob: tool, person follow, args, target, phone, queue in the paper maps that to a behavior tree node.
The node then ticks its plugin. For the person tracking module, we YOLO V11 the camera frame, pick the centroid, hand off to the velocity controller, and publish a /kmb vel.
And because the tree ticks at, say, 10 Hz, if YOLO drops a frame, the fallback lost subtree kicks in, rotate until reacquire or timeout. Deterministic recovery, no panicking.
From the user side, that means if the drone can't see the person, it literally says, I've lost them, rotating to find them. Transparency builds trust.
I'm hearing trust, determinism, but what about latency? Business folks worry, will my warehouse robot freeze waiting for GPT to respond?
We measured cognition latency 2.5's median on GP4o. Dispatch is negligible. Execution dominates only when the requested action is long, like a 10-meter traverse.
For a fulfillment center, 2 seconds is fine. Operators already wait longer for barcode scans. It's the long-tail errors that cost margin, not the extra second per command.
Plus, you can cache typical intents. The LLM only needs to run for novel instructions. Common verbs hit a local pattern matcher.
Exactly. Edge computing heuristic. Push the 80% frequent intents to an on-device transformer. Keep the big model in the cloud for the weird stuff.
Let's ground this in a business case. Logistics, healthcare, retail, pick one.
Okay, retail. One chain piloted this with stock-checking drones. Store associates literally said, find empty cereal shelves over voice. The drone interpreted, used object detection, and flagged restock events. Shelf availability improved about 18% month over month.
And associates reported less cognitive load, no tablets, no learning curve. As the saying goes, the best interface is no interface.
Quick note, we used behavior tree conditions to block flight near customers. Safety first. The LLM couldn't override that.
That's the strategic genius. Policy encoded as tree conditions, not buried in a prompt.
Love it. Deep dive number 2, failure reasoning. How does Pive actually work?
When a node returns failure, we capture the driver's low-level error, say, IMU tilt 15 degrees. The LLM is prompted, translate, IMU tilt over threshold while executing takeoff. It replies, cannot take off because the floor isn't level.
Users hear a human-readable explanation. That closes the mental model gap.
And we log that explanation alongside telemetry for postmortem, bringing observability to robotics, finally.
From a compliance standpoint, that's big. Regulators don't want the model decided. They want a breadcrumb trail.
Any contrarian takes? Something we're all ignoring? I'll throw a curveball. Everyone's obsessing over LLM reasoning, but the real bottleneck is perception. If your person detector can't separate twins, no amount of behavior tree elegance will help. Garbage in, garbage out.
That's fair. We see 94% accuracy overall, but perceptual noise was the main miss.
So the next frontier is multimodal grounding. LLM with vision language models tightly integrated, not just bolted on.
We're prototyping VLM-enhanced tools, but watch compute footprint. Embedded GPUs have limits.
Speaking of scale, how do you add new behaviors without redeploying everything?
Each plugin is a ROS2 package. Drop it in, update the tool description in the prompt, restart the LLM interface node, done. We added hand gesture control in a day.
It's like adding a new chess piece, not rewriting the board.
Quick business metric. That kind of modularity shaved roughly a quarter off integration timelines in our pilot programs.
Inter-expert riff time. Do you see any tension between UX simplicity and technical rigor?
Totally. People say go that way, no units. Engineers want centimeters. We resolve by letting the LLM ask follow-ups only when essential, otherwise assume defaults.
But those defaults have to be conservative. I'd rather the robot move 0.5 meters than 5 meters if uncertain.
We encode that in the prompt. When unit ambiguous, assume small. Works surprisingly well.
Adds a tiny friction, saves a lawsuit, an easy trade.
Let's hit future implications. Multi-robot fleets. How does the architecture extend?
Each robot runs its own BT but shares a swarm-level coordinator. Think distributed blackboard. The LLM can reason globally. Robot A, fetch, Robot B, follow, then inject sub-goals locally.
We've demoed that with 3 drones. The coordinator allocates tasks, local trees handle execution. If a drone drops, fallback reassigns in under a second.
And that's where we might swap GPT for a smaller llama on-prem to avoid bandwidth choke.
Famous quote moment. Who's got one?
Plans are nothing. Planning is everything, Eisenhower. Behavior trees are the living plan. The LLM is the planner.
Nice. And I'd add, trust is earned in drops and lost in buckets. Transparent explanations earn those drops.
Let's wrap with lightning advice. 1 line each, business or tech. Start small. Prototype with a single behavior tree branch and 1 plugin, then iterate.
Instrument everything. Status, tick rates, failures. Otherwise, you're flying blind.
Designed for conversation, not commands. Users will speak like humans, not SQL.
Version your trees and prompts the same way you version code. Get all the things.
Finally, measure outcomes in customer-centric terms. Speed, accuracy, satisfaction, not just model metrics.
Brilliant. That's all for today. Remember, robots you can talk to and understand aren't sci-fi anymore. They're shipping code. Thanks for listening, and catch you next time on AI on AI. Welcome back to part 2. Let's roll up our sleeves and dive deeper into how you actually wire this framework into a live production floor.
I'll kick off with the plumbing. ROS2 Humble is the backbone, and every capability is a standalone node. Think microservices for motors. The driver package publishes a CMD vel, the BT core subscribes, and the LLM interface sits on a task topic acting like mission control.
Building on that, the key contract is a tiny JSON schema. 1 field for tool, another for args, optional guard. Keeps the LM output deterministic and parsable, no regex gymnastics. We even set a max token budget of 120 to reduce latency spikes.
And don't forget prompt engineering. We embed tool descriptions plus hard constraints. Never call land unless altitude 0.5 meters. That acts as a safety fuse, similar to circuit breakers in power grids.
From a UX lens, we route follow-up questions through a low-latency speech recognizer on device. So if the user mumbles, go there, the system responds, could you clarify target location within 400 milliseconds, fast enough to feel conversational?
For business folks, the takeaway is modular risk isolation. A hospital can add a disinfect plugin, UV lamp control, without touching navigation code. Regulation teams sign off on that single node rather than re-auditing the entire stack, cuts certification cycles by roughly a third.
Nice. Could we walk through a concrete deployment roadmap, say for an agricorp wanting crop monitoring drones?
Step 1. Flash the drone with our ROS2 image. Includes driver BT and a dummy LLM node. Step 2. Swap in a multispectral camera plugin. Step 3. Extend the prompt with a new tool, Scan Crop NDVI. Total dev time about 2 sprints.
Technically, that plugin publishes a scan done Boolean. The BT waits on that success status, then transitions to an upload results node. 0 custom state machines.
A field pilot this spring showed an 11% boost in yield predictions because the agronomists could literally say, scan the northern quadrant for heat stress, instead of scripting coordinates.
And they loved the transparency. If weather turned windy, the BT's fallback aborted the flight and told them, wind exceeds 6 meters per second, mission paused. No black box behavior.
Let's zoom into the vision stack. YOLO V11 was mentioned. How do you keep frame rates high on modest hardware?
2 tricks. 1. We reduce input resolution to 416 x forward 16 during detection, but keep a high-res tracker like KCF for follow-up frames. Detection runs every 10th tick. 2. We offload heavy tensor ops to the onboard TPU. Edge acceleration saves 40% energy.
And we gate the whole perception chain behind a semaphore. So if the GPU is saturated, the BT temporarily throttles tick frequency from 10 Hz to 3 Hz. Graceful degradation beats a hard crash.
There's a fun heuristic here. Perception speed equals 1 model size times frame rate. Keep that product under a certain constant for real-time guarantees.
I like that rule of thumb, but, contrarian moment, I'd argue many warehouses don't need heavy CNNs at all. A LiDAR-only module with simple clustering can handle 80% of follow tasks at 1/10 compute.
That's provocatively true. Sometimes we chase flashy vision while inexpensive sensors hit the KPI. Remember, function over fancy.
Quick drill down on failure reasoning. How do you map low-level driver codes to human language?
We maintain a dictionary, code plain English template. When a driver throws E12, we attach motor current spike. The LLM fills context. Left servo exceeded threshold during turn. Keeps explanations concise, yet informative.
And we log both the numeric code and prose, so analytics teams can run SQL on failures while operators read the layman's text. Dual surface observability.
Pragmatically, we bundled that dictionary into a ROS2 parameter server. Hot swappable without redeploying containers.
Let's hit multi-robot. How does task arbitration work when 5 bots hear the same command?
A lightweight MQTT broker tracks capability manifests. The LLM reasons globally, selects the least busy robot, then publishes a unicast take task message. That robot's BT inserts a new subtree on the fly via a dynamic loader.
We use a Blackboard pattern as shared memory. Status writes get broadcast to peers. If a robot enters error, the coordinator requeues its tasks. Average reassignment latency, under 800 milliseconds on Wi-Fi 6.
That dynamic loading leverages ROS2's composition API. No reboot, just load the shared library, remap topics, tick.
From operations view, that means floor managers ask, who can fetch pallet B, and whichever robot blinks green first owns it.
And ROI is immediate. Utilization rates climb because idle time plummets. We saw a pilot in 3PL where fleet efficiency bumped roughly 22% after rolling this out.
Security question. What's to stop a rogue prompt from forcing a drone to, say, land in the river? Multi-layer safeguards. First, BT conditions, geofence must be true. Second, driver sanity checks. Altitude sensor must read 0.5 meters to execute land. Third, a policy LLM running server-side flags disallowed intense defense in depth.
Plus, we sign plugins with a checksum. The BT refuses to load unsigned modules. Supply chain integrity solved.
And voice authentication adds one more ring. Robots obey only whitelisted voices. Same trick as smart speakers, but tuned for industrial noise.
Let's sprinkle another business story. Healthcare this time.
A mid-size hospital deployed service robots for late-night pharmacy runs. Nurses speak, "Bring 2 units insulin to ICU 3. The LLM parses quantity, destination, urgency tag. Behavior tree ensures elevator access is clear before rolling. Medication delivery times dropped nearly 30%.
And the robots explain delays. Elevator occupied, waiting. Transparency reduced staff frustration. Soft ROI that matters.
Under the hood, the elevator check is a condition node querying building IoT sensors via Modbus. Same BT structure, new sensor source.
Fantastic. Parting tech tips for teams starting tomorrow?
Prototype the behavior tree graph visually first. Whiteboard it, then code. Visual clarity prevents logical dead ends.
Use unit tests for every plugin. A failing node should not pull down the entire tree. Mock your drivers.
Profile your LLM calls early. Latency surprises are expensive to fix at scale.
Involve real users by Sprint 3. Language ambiguity surfaces only in the wild.
And remember Peter Drucker's line, "There is nothing so useless as doing efficiently what should not be done at all." Pick use cases that truly need natural language, not gimmicks.
Mic drop. That wraps our technical deep dive. Thank you all, and to our listeners, go build robots people actually understand. See you in the next episode of AI on AI. Before we sign off, let's crystallize today's takeaways. What's the single biggest innovation our audience should remember? Hands down, it's the marriage of LLM reasoning with tick-based behavior trees. That fusion bridges fuzzy human language with deterministic control at about 10 Hz without rewriting state machines.
I'll add, the plugin architecture acting like an app store for robots, drop in YOLO, swap for LiDAR clustering, or inject a UV disinfection node, all hot-loaded through ROS2 composition.
From the user experience angle, the explain my failure loop is gold, turns cryptic error codes into plain language, which slashes downtime because operators troubleshoot in minutes, not hours.
Operationally, the lightweight MQTT Fleet Manager plus dynamic subtree loading keeps multi-robot orchestration under a second, so tasks never sit in limbo.
Strategically, remember the rule of 3, transparency, modularity, and auditability. Nail those and regulators, insurers, and end users get on board faster. Seen it cut deployment timelines by roughly 25%.
Lightning round caution. What's the most common pitfall teams trip over?
Overprompting the LLM, more tokens equal more latency, so prune that context window early.
Forgetting safety guards in the prompt. Never trust raw natural language without hard constraints in the behavior tree.
Skipping real-world voice or dialect testing. Linguistic nuance kills demos if you ignore it.
Ignoring compute budgets, edge TPUs are cheap insurance against frame rate collapse.
And chasing bells and whistles. Solve a real pain point first. Pharmacy runs, pallet moves, crop scans, then scale.
Perfect. To quote Da Vinci, simplicity is the ultimate sophistication. And today we saw how simple, modular building blocks unlock sophisticated robot behavior. Huge thanks to our panel and to all of you tuning in. If this episode sparked ideas, drop us a note. Until next time on AI, keep innovating and keep it interpretable.